So you're basing your argument on the uncertainty principle, which is the core of quantum mechanics. So let us recall what this principle says. Think about a classical object, say something being thrown in the air. So at each moment you know that object, its position and momentum as precisely as you want. Not so in quantum mechanics. In quantum mechanics you can know the position of a particle, but then you don't know its momentum. It has many velocities at the same time. You can say, I want to measure exactly its velocity, that is its momentum, and then you know its momentum. It's going this way and at this velocity, this is the mass, but then it has many positions at the same time. So you say that this uncertainty principle is what gives us, you base your argument on free choice on this uncertainty.
Heisenberg came with a very before Schrödinger, with a very complicated mathematics. We don't have the possibility to go into it now. I just mentioned for people that know about it. He discovered the position momentum of particles by matrices and write new equations of motion, called the Heisenberg equation of motion, for these matrices. And that's how you could predict what happened to the particle later. But it turns out it was extremely complicated to solve these equations. Then Schrödinger came with the idea that indeed each quantum particle, just like the classical wave, has properties of particles, these quantas. The body said, okay, maybe classical particles will have also waves. And Schrödinger took this idea and wrote the famous Schrödinger wave equation that describes now the motion of quantum particles by saying that each particle, instead of being a point, like in classical physics, is described by a wave. Wave is different. Each particle has a wave that is different from zero in all locations of space. But what is the meaning of it? The meaning of it is the size of that wave tells you what is the probability to find the particle in this location. Historically, after Schrödinger wrote his equation just a few months after Heisenberg, because it was so simple to solve this equation, everybody left Heisenberg and went and discussed and solved all the problems of quantum mechanics, atoms, etc.
To this day, people prefer the Schrödinger.
Because it was so simple mathematically. And because because of that, they thought that indeed that is the correct way to think about what happened in quantum mechanics. That because the mathematics was so much simpler.
Now you're
but Heisenberg said, no, it could not be right. That could not be the true physics. But nobody knew even how to think in the Heisenberg language about the two-slit experiment.
I must confess, I mean, most quantum physicists use the Schrödinger picture because even in the case that you are describing, the electron which goes on two paths, the best way to understand why it goes only to this side and never to this side, this side, is to think about a wave. The wave makes constructive interference in one side, destructive interference in another side, just like sound waves, water waves, all other waves. And now you come, let me just tell our viewers, and you try to restore the particle picture of quantum mechanics after so many years that people have been using the Schrödinger picture. And to this day, of course, we had many discussions about that, but it's about time to say, why do you want to come this full circle and restore the particle picture? We are all used to the wave-particle duality, and we are all used to think that it's both wave and a particle. There are several experiments that show that every quantum is a wave. And on the other hand, there are several experiments, Einstein's photoelectric effect, which shows that it's a particle, and they're equal. And you're perhaps the only one who say they're not equal. There is some advantage to the particle picture, which this is why I, Yakir, prefer the Heisenberg formalism over the Schrödinger.
Let me say the following. People tell the story about quantum mechanics in a way that says, look, it's so mysterious that we will never really be able to understand it. We have to rely on the mathematics to tell us what's happened. I come and say, look, you tell me a story. The story is that electron, a single electron that has a given charge and a given mass, can be a wave that is spread all over space. The question is now, how do we think about this wave? If we think about it as really like classical wave, that means that the charge and the mass of the electron is spread all over space. Now, suppose it's true, I come at a given time, make a measurement, and find the electron at a given position. Now, immediately, all the charge and all the mass are now located at that position. And instantly before, it was spread all over space. How could this charge and mass collect very quickly to this position without producing any strong electromagnetic radiation, etc.? It cannot happen. That story cannot be right.
So you're against the notion of collapse? No,
I'm not against the world. I'm saying that the collapse has to be explained in a new way. Wait a minute. Anyhow, there is another possibility to think about that wave by saying that actually the particle is always only at one location, we don't know where, but this location, while it is in this location, it has also other properties that later will become local properties. And now they are not local, but they are sitting on the particle. So the particle has properties that can be affected non-locally by something else, and that is another way to think about the wave. Let me tell you a very interesting historical story. In 1964 or 5, I'm not sure, I was invited to come to Munich to visit the Max Planck Institute. At that time, Heisenberg was alive, still for a few more years, and people told me, his assistant, in fact, Peter Dew, met me and asked me what I'm working on, and then he said, I think Heisenberg would like to meet you. So he introduced a meeting between me and Heisenberg. I came to the office of Heisenberg. I said, Professor Heisenberg, how do you think about the two-slit experiment in your language? I said, I don't know how to do it. There must be some wave there.
Heisenberg said that.
Yeah.
So even Heisenberg confessed that his picture is not adequate to explain the double-slit experiment. And now
either not adequate or he does not know how to do it. He did not know how to do it.
And you?
So I taught him how to do it. I told him, look, Professor Heisenberg, I showed my new way to think about the non-local Aharonov bomb effect as an exchange of something that I call modular momentum. I don't want to go into technical details, but anyhow, the basic idea was the following. The particle goes through one slit, it knows whether the other slit is open or not, by having another variable in the particle later, which is the particle on which place in the photographic plate to appear, but right now that variable cannot be measured locally, but it can be affected by the question whether the other slit is open or not. It's a little bit complicated, but it is really the right way to think about quantum mechanics. And the right way is also because of the fact that I develop a new formalism in quantum mechanics where I say that the particle at a given time has to be described by two boundary conditions. By measurement was done on the particle in the past that developed to the present, and also by the result of a measurement that will be done later in the future that comes back to the present and affects also the behavior of the particle. In this way, for the two-slit experiment, I was able to show that from the past, the particle has this non-local property that tells it whether the slit is open or not, and from the future, I can find out through which slit the particle went.
Okay.
So it's a little bit complicated, but anyhow, the idea is you have two possible pictures of quantum mechanics, two possible stories. One story is to say, look, It's very simple. It's exactly like the classical wave. We are very trivial and intuition about it. The particle can be a wave, and that's why when you go to sleep, we have destructive interference. Beautiful. But then once you tell this picture, there are always all time with new surprises that come all the time, and people don't understand really deeply what quantum mechanics is all about because they don't have the right story. I claim that the right story is the story that a particle is always just a particle, and it has also properties that are affected non-locally and affect non-locally, and they replace that picture of the wave.
Let me